Hi, here we are in our third lesson in our chapter on correlation and linear relationships. Today we're going to discuss a numeric measure of how well a line is suited to a set of data. We're going to be looking at Pearson's correlation coefficient, it's called. Normally we refer to that by the variable r. And what that is, it's a unitless measure that tells how strong the correlation between two variables is. It's on a continuum, folks, with the smallest value possible being -1, the highest possible value being 1, and right in the middle, of course, 0, which would mean that there's no association or no correlation. A -1 represents a strong negative correlation or a strong negative linear relationship. So if we were going to have a correlation coefficient that came out to be -1, folks, that would be a steadily decreasing line all the way down right in line, a strong negative linear relationship. On the positive end of the spectrum, if we had a scatter plot that looked like this, with a line that totally kept increasing, that would get a Pearson's correlation coefficient of 1, which means that there is a strong, again, but this time positive linear relationship. Now, since we are on a continuum, there are obviously other values of r in between -1 and 0, 0 and 1. Strong relates to being at either end of the continuum. So something that was called like -0.7 might be called moderately strong. If you are down here around, say, 0.2, relatively weak, right? A 0 means there's absolutely no correlation, and a scatter plot has to show no pattern, no linear pattern at all. Okay. You probably are familiar with the value of r. I believe that you talked about that in your Algebra 2 classes. So today we want to be able to talk intelligently about the Pearson's correlation coefficient, and I'd like to start by showing you a formula for finding that value. Oh my word, look at the math there, folks. It looks awful, but I'll tell you, 1 over n minus 1 should remind you in the standard deviation calculation. Remember, since we were talking about a sample only, we subtracted 1 from the number of data items, and that's exactly what this is showing. The summation symbol we're familiar with, but as you take a look at these two parentheses, x minus x bar over s, folks, that's the z-score, right? That is the formula for the z-score. In this particular case, it's the z-score of all of the x values. That's multiplied by the z-score for all of the y values. That looks like nasty math, but when you break it down, it's really not so bad. However, most of us are going to appreciate that we don't have to do that every time. Our calculator can display us the correlation coefficient. It's shown in the linear regression screen. So this says that we should make a scatter plot, estimate a value of I, and find the regression equation and a value for r. Well, making a scatter plot, we can do that on our calculators for sure. And so I'm going to go there, and then I'll just sketch my plot when I'm finished here. I'm going to go ahead and enter that data into the list. You should pause the video and do the same thing, and I'll catch up with you in a minute. And I'm going to go ahead and set up for a scatter plot. Second and y equals. My plot is turned on. It's looking at list 1s and 2s, which are good. That's where my stuff is. I have a window set up that takes GPAs, or the x value, from 70 to 120 by 10s. The y's these are GPAs, from 2 to 4.5 by 0.5. Let's take a look at that plot, and we'll just give it a quick sketch here. In general, I think that you could say as IQ increases, there's a positive trend. GPA goes up, but that certainly is not a strong correlation at all. Again, the window that I had went from 70 to 120 in IQ, and from 2.0 to 4.5. Now I'm not going to try and plot all of these, but I am going to just try and show the general pattern. One real low guy there, and then two higher up here. All right, again, a rough sketch is all we're asking for. Based on this, I would estimate the R to be positive for sure, so greater than 0. However, this does not look real strong to me. I'm going to say something moderate, perhaps, around 0.7. You may or may not agree with me. Let's next find the regression equation and the value of R that the calculator says. We've made our estimate, but what does it say? Stat, and over to Calc, and we're going to choose LinReg and go ahead and enter through if everything is okay for you. Yes, here's our regression equation and a value for R. So if your R is not showing up, I want to circle this on my screen. You can find that function to show R and turn it on this way. Second and 0, which is your catalog of functions. Look for diagnostics on and hit enter twice. After that, you should get it every time. So to the nearest, say, 10,000, so I'm going to round things here. Ry should be equal to about 0.033033x minus 0.358 approximately. The R value that the calculator has is around 0.664, and that's not too far off from what we had predicted. Let's take a look and see what this equation looks like with our data. So vars 5 over and EQ, and let's graph again. Oh yes, here we are. We're sloping up here, and you can see we could sketch that in pretty easily here. However, our sketch would be a rough estimate, and theirs, of course, is more precise. So the value of R tells us that we have a fairly strong linear correlation. 0.7 is positive, so our slope is positive on this line. And we have some points that are far from the line, but still a positive and fairly strong correlation. There is one more way to measure the goodness of fit for a least squares regression line, and that is called the coefficient of determination. We define that as R squared, and some of you may have noticed that it's found in the linear regression screen. So on my calculator, I'm going to have to go back and calculate that again. Stat, calc, and 4. And just go ahead and arrow through everything as long as you're good and calculate. And here comes our R squared. Notice that it is about 0.441. It's just found by taking the value of R, raising to the second power. The coefficient of determination tells you the percent of variation in Y due to using X as a predictor. And I'd like to put that in some terms that maybe make a little bit more sense to us. What it's saying is, in the example we're looking at, GPA varied a lot, but the percent of variation in our GPAs due to using IQ as a predictor was about 44%. Okay, about 44% in our example. About 44% of variation in IQ, or in GPA, sorry, in GPA is due to using IQ as a predictor. So if r were to, in some other data set, be 0.9, then r squared would be 0.81. That would be the coefficient of determination, and it would mean that 81% of the variation in the data set can be attributed to using x as a predictor value, or a predictor variable. Now, that's all good and well, but what's really interesting to me, if 81% of the variation comes from using x as a predictor value, the rest of the variation, in this example case, 19%, must be due to random chance, or there could be other factors. You remember those lurking variables. Lurking variables. So I'd like us to think about that in terms of our example. From our previous example, r was about 0.664. So the coefficient of determination was around 0.441. That means that around 44.1% of the variation is due to using IQ as a predictor. But the rest of the variation, so 100% minus that, or 55.9 of the variation is due to other factors, or could just be random chance. Some of the other things that might be at work here, well, think about it. What goes into establishing a GPA? It's not always how smart you are. It's how hard you work, right? So it could be work ethic. Although work ethic doesn't really affect IQ, it certainly affects GPA. Other things that might be at work ethic, time spent, or the time factors, stress can have stuff to do with GPA. There are all kinds of things, lots of things that might also be affecting GPA, not just the IQ. It isn't all about smarts, although that's a large part of. So anyway, I hope that that was an interesting discussion for you. I love thinking about things like this, and I hope that in class maybe you'll come up with some things that I didn't think of. So get out there and try that. You try, and we'll see you in class tomorrow.